would be little r squared plus z squared square root. Okay. All right, so we're almost there, actually. So now, next thing is dq. How much charge will be found within this ring of radius r and length dr? Okay, so let me write it this way. So you're saying dq would be eta times the area, right? Which is, let's call it dh. How much area of that ring? And the area of a ring and of a ring would be what?
2 pi r times the length? Oh, wait.
If the ring is full, if it's a circle, it would be pi r squared, but I'm just looking at this area.
Oh, 2 pi r?
2 pi
2 pi r
Times
times dr. Yeah. Remember the way I think about it? This is a circle, right? Always think of it this way. Suppose I take that ring and cut it and open it up. So when you cut it and open it up, this ring, this strip, it would be or this ring would become a long strip like so. Since this is r, when you open it, this is the circumference of that ring, because when you twist it back, you get the ring. So this is 2 pi r. And this is the thickness, dr. So the area is length times width for a rectangle. So 2 pi r dr, that's the area. So dA is 2 pi r times dr. So replace dq by this, and now you're ready to go. So you have this, dv equal to 1 over 4 pi epsilon naught, and then r squared plus z squared square root, and then dq. But dq is this, is eta, and then 2 pi, and then r, and dr.
Are we not getting rid of data? Like changing that into Q
Over the area? Well, we can do that, but for now, let me leave it as eta. Yeah, definitely. We can write eta as the total charge over the area of the disk. Let's leave it eta for a second. Now, 2 pi over 4 pi is just 1/2, right? So you will get, you will have just eta over 2 epsilon naught. Yeah, eta over 2 epsilon naught. And then what remains is, here is r dr and all this stuff. R dr over r squared plus z squared. Now, this is dv. I want v, so I need to integrate. Sum them up. My rings will start from really tiny ones, a radius of about 0, all the way to the one on the edge, which is radius capital R. So I go from 0 to R, right? From 0 to capital R. So my V would be this. That's theta over 2 epsilon naught. Integral now from 0 to capital R. I mean, again, eta and epsilon naught, this is a constant, so it comes out from the integration. And you have r dr over r squared plus z squared square root. So you can use U substitution, or you can kind of think about what the antiderivative should be. Would be eta over 2 epsilon naught. We encountered this before. So what's the integral of this? Huh? ln? Not quite.
No, it's
Not quite, yeah.
2 times 1 over
0.
square root.
You can do, not quite 0. I think, you said the trig, I guess you can use trig, but it's simpler than that.
It's a use of.
You can use a U substitution. Yeah, go ahead.
Oh, would it be 2 over square root of r squared plus z squared?
It will turn out to be this. R squared plus Z squared square root, that's it.
Oh, because it's, yeah.
Because when you take the derivative of a square root, you get 1 over 1/2 times 1 over the square root, right?
Yeah.
Because it becomes something to the minus 1/2, so it's just square root over. And then the chain rule will give you a 2r. So the 2r cancels the 1/2 that comes from the square root, and that's your r.
Oh,
right
okay,
there.
thanks, that makes sense.
So, again, take this derivative with respect to r and you will get that. But we don't forget the limits from 0 to capital R, right? So you will get eta over 2 epsilon naught times. When you substitute capital R, you get r squared plus z squared square root. You get capital R squared plus z squared square root minus what?
Z.
Yeah, when you substitute 0 for r, you get just the square root of 0, the square root of z squared, which is
Z.
z. Technically, it's the absolute value of z, but z is positive, so yeah. Okay, and that's it. Yeah.
Isn't it the integral like 2 times the square root?
I'm sorry.
I think the result should be 2 times the square root of 1 squared.
You think that there should be a 2 here?
Yeah.
I don't think so. When you take the derivative of something to the 1/2, you get 1/2, right? If you, yeah, let's do it quick. ddz of this, ddr of
There might be.
r squared plus z squared to the 1/2, right? Because the square root is to the 1/2, right? So let's do it. So you will get 1/2, and then r squared plus z squared, right? To what power? You have to subtract 1, so what? Minus 1/2, yep. And then the chain rule would say, take the derivative of this, which is 2r. So you will get r over the square root. So it should be, yeah, it works. Yeah. And I'm positive it works because I have the 8 over 2 epsilon naught, which reminds me of the electric field. So, yeah. All right, so yeah, let's continue with. Can I erase this side work here?
Yeah.
Don't think I. Yeah. Oh, let's just summarize here. So V is eta over 2 epsilon naught, and r squared plus z squared minus z. Okay, that's it. This is for a disk, right?
Can we just change the area to the initial, yeah, how many zones?
Oh, you want me to change eta to q? Yeah, so eta is q over pi r squared, right? So you would put the q over 2 pi r squared epsilon naught. Yeah, but I want to leave it like this for a reason. I want to connect them with the electric field. Yeah. So that was basically, in many ways, the end of chapter 25. And we already started chapter 26, except I just didn't say it was 26. Because 26 says, hey, you integrated E. What do you have? You integrated the electric field to get V. So what do you have to do to V to get E? You have to take the derivative. That's what we're going to do next. So the connection between E and V. So we said delta V is you have to integrate E dot dr, right, with a minus sign. So V, or the electric field will be minus dVd. Let's say if V is a function of x, then the x component, you'll just have an x component of the electric field, dV dx. dV dx, right? Just like when we had the parallel plate capacitor, the electric field was in the x direction. And so, that's what we have. How about if, before I even discuss that, let's take this and go with it to a charged ring and a charged disk. But here's your homework for the next, let's say, 3 minutes. if you have a book, if you have notes, let's please look up the electric field for a ring and the electric field for a disk. We derived these expressions, they're in textbook, chapter 23 probably. And so we want to write them down first. Yeah,
I have the one for the ring.
you have that, okay, yeah.
Yeah, I have Q times Z over 4 pi epsilon naught. And then C squared plus R squared to
Z
the
squared?
Yeah, it's C squared plus R squared, capital R, to the 3 halves. Like that, the parentheses, yeah.
Like so?
Yeah.
Thank you.
And
For the disk,
and over to epsilon naught.
8, alright? Over 2 epsilon naught, that's why I wanted to.
And then bracket 1 minus
1 minus.
z over r squared plus z squared and square root.
Like this?
Yeah.
Okay. So these we got a while ago. And you may remember how we got them. We had to take the cosine and argue that by symmetry, anything besides the z-axis would cancel out. Yeah? We remember that? Did I?
Sorry, but what is the letter on top of the square root of R squared plus Z squared?
Here?
On the bottom. Yeah.
Z?
Oh, it's Z?
Yeah.
Okay, but yeah, I'm sorry.
Yeah.
There's a lot of Greek letters, sorry. So I'm not sure.
I always put a bar to
Okay.
distinguish it from
Thank you.
2. Okay. Yeah. By the way, needless to say, if I make a mistake, please tell me ahead of time. Because we would have to come back for a while, like, you know, rewind and go back. So, okay, so ready? Okay. So that's if you had the potential dependent on the x or on x. If it depends on y, then you would have minus the y component will be minus dv dy, and if you have the potential depending on z, I mean there is nothing sacred about x. It can be called z. So dv dz. So for both the disk and the ring, we chose the axis that we're working with to be the z-axis. So we have our disk, we have our ring. So what we're going to do is do negative dv dz, not dr, dz, and see what we get for the electric field. All right, so here's, let's do the ring. So we got v for the ring. I'm going to just copy that expression. It's 1 over 4 pi epsilon naught. Let's put the q here. And then 1 over r squared plus z squared square root, right? So let's see if the electric field is minus dv dz. So I'm giving you a moment to do this derivative with respect to z on your own and see if you get this thing here. So I'm going to give you a second to do it. And then we'll do it together. By the way, I will need these 2 words in a minute, so if you want to write them down. Okay. Did anybody double check that you get that?
Yes.
Yeah, is it? Okay. So let's double check it. So you get minus. We're taking a derivative, so this constant does not matter. Let me put it in front. So minus, here is q over 4 pi, epsilon naught, and then d dz of this, right? This is what I'm taking the derivative of. This is r squared plus z squared, and then there is a square root, and it's on the bottom, so it's really r squared plus z squared to the minus 1/2. And when you take the derivative of something to the minus 1/2, let me leave my negative q over 4 pi epsilon naught here, minus q 4 pi epsilon naught out there. And then let's take this derivative. When you take derivative, the minus 1/2 comes down, so it becomes minus 1/2. And then you multiply by r squared plus z squared. You have to subtract 1 from this. So minus 1/2 minus 1 is minus 3/2. To the minus 3/2 r squared plus z squared. And then you have to take the derivative of the inside function. R is a constant, so that goes away. And then so derivative of z squared is 2z. So 2z. Sorry, got squeezed there. And so we get, let's see, e would be, you got a minus times a minus, that's a plus, so everything becomes a plus. You got 2z and the 1/2, so the 1/2 and the 2, they cancel each other. So you have this, q over 4 pi epsilon naught. Again, the minus sign went away with the other minus sign. And then r squared plus z squared to the minus 3/2 is r squared plus z squared to the 3/2. Just put it on the bottom. And then there will be a z, right? This z will be on top of it. And so we got that. So it works out. QZ over all that stuff. The next one is to look at the potential for a disk, and we have to take the derivative with respect to z again and see what we get. So let's do that. And again, can I erase those two boards over there? Any objections? Okay. Yeah. Give me a second to do it. I'll just copy the. Oh, this is V, right? So let's take the derivative. So you got the electric field. It will be minus dV dz. By the way, why don't we take the derivative with respect to x and y? Or what does it give us if I take the derivative with respect to x and y? I get 0, yeah. It means I don't have an x component or a z component in that case, or a y component, I just have the z part. So I have minus eta over 2 epsilon naught, that can stay in front, eta over 2 epsilon naught, and then d dz of all this stuff here. R squared plus Z squared. I will write it to the power 1/2 instead of square root, so it becomes clear to us. And then minus Z. So as you take this derivative, you will get minus eta over 2 epsilon naught. And then the derivative, the 1/2 comes down, right? We have the 1/2. And then R squared plus Z squared to the power minus 1/2, right? You have to subtract 1. And then times the derivative of the inside with respect to Z, so you get 2Z. 2Z. That's it. And then minus what? What is the derivative of Z with respect to Z?
1.
1. So you can now, this 2 and the 1/2 will cancel each other. And you would have E is equal to. Now put the minus sign inside. So this negative 1 becomes in front, becomes plus, and this positive becomes minus, right? When I drive the minus sign inside. So I'll get eta over 2 epsilon naught. And then I have 1 minus. Let's see what we have here. I would have Z on the numerator, and then this to the minus 1/2 goes downstairs, and it becomes the square root. So Z over R squared plus Z squared square root. Yeah, they match. So that's good. Yes.
What's the parentheses after the to the negative 1/2 power? There's like another parentheses.
This one?
Yeah.
2Z.
2, oh,
2 times. Any other? So just to summarize, in general, if you have the potential, function, right? It would be a function of x, y, and z, maybe 3 different variables. And so in that case, you would have this. In general, just to summarize it. In general. The x component of the electric field will be minus dv dx. The y component of the electric field will be minus dv dy. And this curly v means partial derivative, because you might have more than one variable. So it means hold the other variables constant except for the one you're differentiating with respect to. And then the z will be minus partial v partial z. And to write the electric field in vector form, it is the x component of the electric field I hat plus the y component of the electric field j hat plus the z component of the electric field k hat, right? And now the x component is minus dv dx, the y component is minus dv dy, and then the z component is minus dv dz. So if you put them all together, you will get, all of them have a minus sign, so I put the minus in front, so you have dv dx I hat plus dv dy j hat plus dv dz j hat. I have one more step to say.
Something to do with the gradient?
Yes. So this this thing here, ddx I hat, ddy j hat, ddz j ddz k hat has an abbreviation, and you can write it as what's called the gradient. And it's an upside down triangle. Or who's to say what's upside down? It's a triangle. Upside down delta.
Now what?
Yeah.
Okay. Yeah.
Downward.
V. Yeah. And yeah. All right. That's the
It's negative.
yeah.
Oh, it's-
So this is if your electric field has X, Y, and Z.
X, Y, and Z. Yeah.
Yeah.
Yeah. So you can construct the function for the electric potential that depends on x, y, and z. And you just have to take its partials. Okay. Now, yeah. So I have a couple things to mention. One of them is just, so we're going to get into circuits pretty soon in the next chapter. And so we're going to mention, we'll talk about conductors a little bit, and then we'll talk about the capacitor, and then we will mention the what's called Kirchhoff's rule. Yeah. Yeah. Okay. So, okay, thank you. So, so here is the potential. So how about if what's the change in potential if I come back to the same point?
Zero.
Zero. Because the field is conservative. Yeah. So for example, potential and potential energy, they're not the same thing, but they're intimately related. It's the potential energy per unit of charge. So let's say here's a chalk. I'm talking about gravitational now potential energy. Let's say I take this piece of chalk, I take it, everywhere. I drive it around and then come back. When I come back to this same point, what's the change in potential energy? Zero. So similarly for the electric field, because it's a conservative function, you have delta V. In general, delta V will be the integral from R initial to R final of E dot dr, right? E dot dr. But if I go around a closed path, so let's say I start here and I come back, I will draw a circle around it. That means closed, integral over a closed path. So this always equals to zero. This will always equal to zero. That's always zero. And we will see this when we do circuits. A circuit, electricity will flow around. And we will choose a point on the circuit, and then when we go around that point and we come back to it, the change in potential would be zero. Okay? And it's called Kirchhoff's, I think, first rule, or change in potential. But as you can see, it's, I guess he discovered it first, but it's nothing but conservation, but the fact that it's the electric force is conservative. So, yeah. First law or something like that. I forget what it's even called. Loop law. Loop law. Okay. Yeah, there is the loop rule and there is the junction rule.
Oh, okay.
Yeah.
It's actually
The
very
junction rule is similar to water. We'll get to it. It basically says if you have current flowing and it splits over here, there is a junction here. The current that goes in must equal to the sum of the two currents that go out. And if you have three currents coming out, what goes in has to equal to what comes out. That's all. And that's just conservation of charge, right? You can have, let's say, 1 coulomb per second coming in and 2 coming out. Or you don't do, yeah. Yeah, and by the way, those are the two rules, and pretty much you can solve any circuit with them. Yeah. We will, after the break, that's what we're going to do. I don't need this. Okay. So now, conductors, just to quickly mention them, we said a conductor in electrostatic equilibrium, the electric field inside the conductor is what? Zero. Yeah, so if it's in electrostatic equilibrium, let's say here is a conductor. This is a conductor. The electric field inside is equal to zero, right? And the consequence of that is if the electric field is zero, then the potential at this point must equal to the potential at this point. Why? Well, look at the definition of the change in potential. Change in potential is the electric field dotted with dr, right? So if E is zero, then E dot dr is zero, and you add infinitely many zeros, you still get zero. So it'll be zero. A conductor would be equipotential, meaning if this part of the conductor is at a potential of, let's say, 10 volts, every other part would be at a potential of what?
10 volts.
10 volts, yeah. Okay. Another thing that we said about a conductor was the electric field is always perpendicular. If there is excess charge, that charge will sit at the surface, yeah. And the electric field is always perpendicular to it. Does anyone remember what the argument was to show that it's perpendicular? It has to.
Was that cosine theta?
It's a cross product, right?
Dot,
Dot
product.
yeah,
Sorry,
that,
dot
yeah. So that's one way to view it. We said if it points in this direction, then it will have a component, and that component will apply a force on charges, and the charges have to move until they get rid of that component. They cancel it. Another way to view it now is to say, if the electric field is perpendicular to the conductor, and I already know that the conductor is equipotential, it means this point on the conductor must have the same potential as this point. So the amount of work done when you move a charge from here to here must be zero. So that means the force on it must be zero. I mean, the work on it must be zero. So the force has to be perpendicular to the displacement. So the electric field will always be perpendicular to the surface of the conductor. And another one is that electric field at sharp corners will be stronger than at broad corners on a conductor, than the pointy corners. Charges will tend to focus more there. So for example, here is a conductor. Let's draw a conductor that looks like this. And then let's say it's, right, this is broad, this is sharp. And the claim is that the electric field here is perpendicular, but it's stronger. The electric field here is also perpendicular, but it has a larger value than here. And the reason is this: for a consider a sphere. A sphere of charge Q. What's the electric field at the surface of the sphere? The sphere has radius r. What's the electric field at the surface? What did you say? Once you exit the sphere,
KQ over.
KQ over r squared. KQ over r squared. It's KQ over r squared. Now what's the electric over r squared? And then what's the electric potential at the surface? Okay, I'm still okay. At the surface of the sphere, what did we say?
KQ over R.
KQ over r, similar to a point charge. So it's KQ over r. That means the electric field is just the potential divided by r. Right? If I divide the potential by r, I get E. Right? Is everybody following me on this one? Right? So if I divide V by R, I will get KQ over R squared, which is E. So E is equal to V divided by R. So that means V is equal to E times R, right? E times R. So notice now, a broad corner, this corner, you can think of it as a part of a sphere. And this whole conductor has the same potential, right? Right? It's at the same potential, so it's the same V. So E times R will be a constant. The product of the electric field times the radius of curvature is a constant. So if the radius of curvature is large, then E will be small. If the radius of curvature is small, then E will be large, so that the product will remain constant. Okay. Yeah. So at sharper edges, it's more electric field, and if there is more electric field, it means the charge density there is actually larger. More charges would be focused here.
Isn't R greater on the corner though?
No, it's because if you consider this as part of a sphere, it will look like a tiny sphere. And this one, if you consider this part as part of a bigger sphere, that bigger sphere will look like this.
Bigger area has bigger.
Huh?
So
If it's bigger,
less electric.
less electric.
Could you go back to when you were explaining those two dots inside your conductor?
Yeah. So if the electric field is zero, it means the potential at this dot, or if I move from here to here, E is zero, so E dot dr must be zero. It means the change in potential must be zero. So it means the potential of this point and the potential of this point must be equal to each other.
And that's why that's 10 and that's 10,
Yeah.
the change.
Right, exactly. The change will be zero. Okay. So there is a, I'm going to go to capacitance and batteries, but let me do one more qualitative example. Here is a qualitative example. Here is a sphere, right? It has this size. Here is a bigger sphere. This is sphere A. This is sphere B. And here's an even bigger sphere, C. I think C is clearly bigger than B, isn't it? Okay, I intended it to be bigger, okay? So all of them are charged, they have charge, okay? So if they're like this, and I say, which sphere has the larger potential? What can you say, if anything?
They're all the same.
Why would they be the same?
Because the greater R, the less E is. No?
I'm being tricky though. I said you have three spheres, they are charged. Did I say they have the same charge?
Oh.
I did not say that. So you have no reason to assume that they have the same charge, and the V is KQ over R. So maybe the one that's larger has a larger R, but maybe it has so much charge that the V will be larger eventually. Okay? So I said nothing about it, so we can't really say anything right now. So now we're going to connect the spheres with a conducting wire. So the spheres are conductors, and I'm going to connect them with conducting wire. So I'm going to connect this sphere with this sphere, and this sphere with this sphere. So they're all connected now, right? And everything is conductive. So if they're all connected, what do I know about their potentials? They are?
Oh, they're all the same.
They're all the same, yeah. It's one conductor now. They're all connected. So charge might flow from one to another, and they just have to adjust to make that happen, to make the fact that they're equipotential. They all have the same potential. So VA and VB and VC, they're all the same. So the conclusion here is VA and VB equals to VC. How about their electric fields? What can we say about EA versus EB versus EC? What can we say?
Oh, A's is the largest.
A is the largest because it has the sharpest corner. There are no corners, it's a circle, but it has the smallest radius of curvature. It has the smallest radius of curvature. So, larger and larger.